Okay, thanks a lot to be here to share our recent works. And my name is Chao. I'm associate professor from the Department of Mechanical and Industrial Engineering at NTU. This work done by the Giuseppe, that's my student, and co-supervised by our collaborator in the Politecnico di Milano, Federica and Laola. This project also supported by the European, that's MSCA GAP project. Now, let me just give you a brief introduction about it. So the motivation of this study is because the extraordinary performance of lattice materials, which received high interest recently. And the advantage of this, lattice materials, it could be the lightweight, it could be have the higher, ultra high strength to density ratios, and also scientists have already found it have the unprecedented mechanical properties. For example, negative Poisson's ratio, negative elastic moduli. However, we also find the challenges in designing the lattice materials because the design process could be very time consuming, and also it needs your prior knowledge for structure property relationship. In order to tackle these challenges, our studies, this is our aim, and currently these presentations were divided into the 6 parts. So I would tell you how to build our database and how we build the graph neural networks. And finally, I will introduce what's the inverse design algorithm. Now, let's first to look at the lattice materials. Lattice materials is still a big families, and it have the plate-based lattice materials, shell-based lattice materials, and finally, it have the strut-based lattice materials. In our study, we focus on the strut-based lattice materials. It doesn't mean that plate-based lattice or shell-based lattice it's not worth to investigate. Vice versa, actually, they have achieved ultra high stiffness or ultra high strength. However, the reason we choose the strut-based lattice is it's easy to have a higher, let's say, design freedom, more easier to design, and also it's easier to fabricate. This is our purpose, or the reason to choose strut-based lattice materials here. And our goal is simple. So how can we explore the vast design space of non-uniform strut-based lattice materials using new findings in the machine learning? In here, I want to show you the first step is how to build the database. The left figures showing the triangular topology and the compressions. And in here, the Ly is fixed for the dimension Lx because it's the non-uniform. So the nodes are randomly distributed, and the Lx, the dimension in the x direction is from 2.5 to the 3.5 millimeter. In here, these preliminary studies, we use the linear elastic models. Therefore, stiffness and Poisson's ratios is the material properties we use in here. The details of our finite element simulations, I would just simply say is that it's run by the commercial software Abacus to perform the buckle analysis and also the post-buckling analysis. Timoshenko being used in here, and the purpose of the buckle analysis was to obtain the lowest eigenmode and the critical displacement delta y. And by introducing the imperfection to the lowest eigenmode, post-buckle analysis was performed to obtain the mechanical response. The imperfection factor was set at 0.01 for all cases. The applied displacement del y was set as 2 times critical displacement. The effective stiffness and Poisson's ratio of triangular topology lattice was defined as the following 2 equations. So this is how we define our geometries and how we data post-process of data. So this is a typical force displacement curve of our simulations. So it's simple that we extracted the linear part for the effective stiffness. We also get our effective strength, and all the detailed that calculations was summarized in here. That's how we get the reaction force, displacement, strain in x and in y directions. Therefore, you can get the effective Poisson's ratio. After we finish building our database, we need to build our graph neural networks. In here, what you can see is that the non-uniform triangular lattice materials discretize nodes and edges. This is the graph representation of lattice. So we use the framework PyTorch geometries to build our models. We have 20 nodes, we have 43 edges, and the input features of the nodes is the node coordinate. And for the edge features, we have the axial stiffness, bending stiffness, nodal displacement. The output results includes nodal displacement, reaction force, effective stiffness, effective strength, and effective Poisson's ratio. The loss functions is included here is only the MAE, the mean absolute areas. L2 regulation technique with the weight decay was explored to avoid overfitting. That's also important. And mini batching technique was also explored in here. The total number of our data is 10,000. Database was built into the 60% for the training, 20% for the validation, and 20% for the testing. So that's how we, build our graph neural networks. After that, we would move to the next step is about the inverse design algorithms. So if you look at here, this is our first step building our FE data, and we build our graph neural networks. And in here, we use the genetic algorithms as the inverse design algorithms to build, that it is. So here, the offspring is, the designs we have. We use the graph neural network as the surrogate models, and we evaluate the performance. After multiple iterations, we would get our final designs in here. And yes, so we build all the three puzzles of our, inverse design algorithms. Now we would take a look at the results. First, let's look at the distribution of the training data. In here, I showing you three figures. Is about the effective stiffness, effective strength, and effective Poisson's ratio. What we could see here is that the distributions, that is close to the normal, quasi-normal distributions. So that's a good signals for our later, data deep learning, study. And in here, I want to show you the prediction performance of graph neural networks. In here, also three: effective stiffness, effective strength, and also effective Poisson's ratio. What you can see here on the right two figures, the prediction accuracy performance is quite, that high. The R-square is over 0.9. The reason here, the effective strength is a little bit lower, 0.8, is because this is a nonlinear phenomenon. And also in here, this is the preliminary studies. So it could be improved later by tuning the hyperparameters of the graph neural networks. But in here, another critical reason is because that it's have the instability and the critical strength is quite close for other cases. Now I want to show you the example history of the inverse design. So what you can see here is also stiffness, strength, and Poisson's ratio. We set our goals is to maximize simultaneously about the effective stiffness, strength, and Poisson's ratio, and we achieve it using only 100 steps to achieve it. In here, the stiffness and the Poisson's ratio, this seems that could be increased monotonically. It's possible. It could be, that if we have a longer step, it could be also improved. But the strength here is almost close to a plateau. This is because you have the upper bound of your lattice materials, which that's set by the series. So this is also reflected in here. Now I want to show you the final result. It seems the screen is right. The final shape is difficult to see. But if we look at the left figures, this I want to show you the first figure is about the inverse design of the effective stiffness and also effective stress. The dashed line areas, this black dashed line represent our original data. So that means is that if the machine learning or the algorithm, what it can see is only these regions. But after we perform the inverse design, that means we maximize our effective stiffness strength represented by these circular symbols, and also minimize, let's say, the effective stiffness strength represented by the square symbols. We can easily to enlarge the design space to this green, that part. This is meaningful because for the traditional design methodology of the lattice materials, normally it's difficult to expand the design space because you have your fixed parameters and traditionally that's it is. But however, using the machine learning methods together with this inverse design, it seems it's much, that's easier and make it work. The second result, what I'm showing you is about the inverse design of effective stiffness and Poisson's ratio. Also, what you can see here is that the black dash circles can be enlarged to the larger ones. One interesting thing or one thing I want to highlight in here is that original data sets, it's always have the positive Poisson's ratio. And from the inverse design, yes, we can achieve the negative ones. This is quite interesting because normally the negative Poisson's ratio and the positive Poisson's ratios, they have the different loading mechanisms. This tells us that for the deep learning method, it is possible to discover some new loading mechanisms, which is difficult or impossible for the human beings to derive equations to get it. So that's also some things I want to say. It's a quite, I mean, that's an interesting point. And finally, I want to show you here also the inverse design of the effective critical stress and also the Poisson's ratio. Similar to the previous result, we can have the much larger design space. It's difficult to achieve by the human being, I mean, that's imaginations. And also here we can achieve, let's say, the negative Poisson's ratio. I mean, that's a negative, I mean, that's a Poisson's ratios materials. So finally, I want to make the conclusions of my of groups, I mean, that study. First, through this study, we can demonstrate the high predictor capability of graph neural networks for non-uniform lattice materials under the buckling load. Second thing I would say that this design space is largely increased by integrating GNN and also graph neural networks and the genetic algorithms. So finally, here I listed the expansion. I mean, that's the details about what is the effective stiffness, Poisson's ratio, buckling strength, which is mainly, I mean, tuned by my by our request. So here is the black ones is the original values, and the red ones is our expanded, I mean, that's the designs. And also in here, highlight again is that we can achieve Poisson's ratios. That means we probably discover some new loading mechanisms in here. And in here, the buckling strength, yes, I mean, that could, I mean, that confirms that this is the upper bound of current designs. But of course, I mean, that's if we change, I mean, that our structures to some different designs, yes, we would also, I mean, that's probably able to get some upper bound limit or the lower bound of our designs. So this is our study. Thanks a lot for your attention and welcome the questions and the comments.